Thank you for having me here. I'm Michael. I'm representing EOS and within EOS, the innovation department. And as in the last years, I've always had the pleasure to demonstrate you the next technologies that EOS is working on. And this year I've brought something with me that I think is very exciting because it is revolutionizing the additive manufacturing industry a lot. Because it's addressing really the main hindering factor of additive manufacturing is cost of manufacturing. So we've developed technology to make everything a lot faster than it has been in the previous world. So I want to come with a little analogy. So what you see here is a variety of different tools that are used to fix, for instance, a broken car. If you have a broken car, the car mechanic in the shop has a variety of tools that he can choose to fix the problem on your car. In additive manufacturing, the tool of choice was always just a hammer. Maybe a 400 watt hammer, a 500 watt hammer, a 1 kilowatt hammer, but a hammer is a hammer. It is not a wrench, it is not pliers, it is not dedicated to fix like a specific problem. So with EOS, we had the vision that we want to have technology that is more tailored to a specific problem and to deliver more energy into the powder bed. So we see a lot of companies coming up with additive manufacturing machines where you have sometimes up to 24 lasers on a system. And we feel this is maybe not the right thing to do because the laser scanner optic components are amongst the most sensitive, most expensive ones. So within EOS, we have developed technology that can transform the beam into any arbitrary beam shape that you can think of. And why we are doing that is because we want to foster a new way of how to melt material. So what you see here is one of our R&D systems that can do this freeform beam shaping. So it's not commercially technology, it is a view into our laboratories. On that system, there's a high-speed camera that can take up to 50,000 pictures per second. So at a very detailed view of what is happening in the melt pool. And we've been able to demonstrate that we can, even with a 1 millimeter spot diameter, so this here is a 1 millimeter spot in diameter, melt Inconel without spatter formation at all. So this is a heat conduction welding. We go away from the keyhole welding, from the deep melting of the powder to a to heat conduction welding. It's a super smooth, very calm process. It has no side products, it has not ejected anything. Now, this is the ultimate goal. We believe here lies the future in additive manufacturing. The problem is, it is not easy to handle that. And it requires beam shapes that are very asymmetric. Now, asymmetric beam shapes face also other problems when it comes to delivering the power, and also the trajectory, the standard trajectory has an effect. And it is not commercially available. So even if you check these different beam shapes, all of them, they have a different formation of spatter. You see it down here, how the spatters are really big and ejected. So we've done really a lot of research into various beam shapes. And we've seen there is already an 80% solution of that technology available. And that is the Enlight technology that we have at first implemented into our M290 system. So the M290 system was the first system that we've modified together with our friends of AMCM, where we have equipped such a laser onto the machine. That is giving us a freedom for research, but it's not really production. For production, we have had the first really high power system built up from scratch. The basis of that system is an M300. The optical bench was completely modified. We have only 4 scanners in there. We have updated it with our latest laser scanner controller optics system, the Sharon 2.0. And we had 4 times 1.5 kilowatt of light inside a very small process chamber. So this is a lot of horsepower in such a relatively short or small process chamber. Now, why did we do that? We think because if we can encapsulate so much heat in a very small process chamber and we can manage to tame the beast, it's an easier thing to scale up onto bigger platforms. The very first thing that we did is we have checked a process transfer. So can we, like on the new generation platform, use existing process parameters, such as Inconel 718, 80 micron Gauss profile, or aluminum, or copper, or whatever material it is? Can we transfer the processes? Then we did infill development to really see if we have so much power, where is the end of it? And then I will show you some applications that are also on display of the exam booth. So the process transfer starts with like building tensile specimens in all areas of the build platform, horizontal ones, vertical ones, density cubes, and we check, can we have a comparable microstructure? Is the density levels in all areas of the platform comparable, and so on? And the answer is yes, they are a little bit different because the scanner and the laser is different, but they are very comparable. So the mechanical properties are good, and they are good enough. We've checked that the microstructure, that the maximum defect size is controlled, that the process results actually show us that on that system, it's even getting better. So we were very positively surprised of how easy the transition is. Same with the mechanical properties. The mechanical properties are in a range where they are at acceptable levels, but this is really just a process transfer. 80 micron 718 Inconel parameters transferred to this system with a lot of horsepower. But I mean, how much fun is it to drive a Ferrari with, like, on a German autobahn with 80 kilometers per hour? If you have a fast car, you want to really unleash the beast. And that's what we did in the infill development. So we did a lot of screenings. And here our engineers, they did very interesting results because they have run 3 to 4 jobs every day with density cubes where they run parameter screenings, because the processes, they are so fast that a job runs only like 2 hours and then the job is already done and you can analyze it. So it was a whole new era of for us to develop processes in a fast pace. Our laboratory was the bottleneck. Our laboratory was not fast enough to prepare all these samples because we were producing so many. Now, what we did is we did process screening with different volume rates. And you have to understand where we come from. On Inconel, on M290, is in the range of 9.2 cubic millimeters per second of what we achieve. With very similar mechanical properties, we are in the range of 17, maybe 18 cubic millimeters per second per laser that we can achieve. And the quality is always a depending function of the customer. So you tell us, do you want to have more like a forged mechanical properties or more like cast grade? Maybe if you can accept a certain remaining porosity, the performance can get even higher. For these 18 roughly cubic millimeter per second processes, what we were able to achieve is extremely high density rates. So the density is like very excellent. It's nearly pore-free. Also in samples that we are generating, which we call parts with like downskin areas or upskin areas. So we see that not even underneath the surface, there's porosity available. We've also checked, which is a very interesting feature of that technology, what is the effect of the roughness, of the natural downskin roughness, just by using, instead of the Gauss beam, the N-Light technology, the AFX lasers. And you can see that directly out of the box, using the N-Light, the porosity and the roughness of overhangs is getting down quite dramatically. Now, with new exposure strategies that have taught us from Smart Fusion how to like really have advanced downskin, we can get this even more down. And if you come to the exam booth, you can see parts with an as-built surface of RA5. So this is really very exciting. So it's great. Also, if the mechanical properties plot, so here you see the mechanical properties over various different machine and system platforms. The N-light lies right there in the middle. So all the mechanical properties from all the different system variants, they are always above the minimum requirements of this AMS 5662 standard. So we are exceeding them. We're always better than the minimum requirement there. But now I want to go into the exciting part, which is, of course, the applications. So here you can see the top view of our M300 process chamber. And inside this M300 process chamber, just for demonstrational purposes, we have one laser operating with the standard 80 micron Gauss, and the other laser with the 250 micron donut beam shape at a lot higher pace. Now you can see how much more material is being melted per time by one laser in direct comparison to the 80 micron existing process. After that layer has finished, I would kindly ask you to have a special view also on the surface, on the shiny surface here, that stays shiny. Even though we are processing at significant higher speed, you have no discoloration here. It appears that there's more process side products being generated, more like smoke being generated, but this is a little misleading. It is not spatter that are flying around and spatter that is being deposited, causing such a dull and like worse appearing surfaces after a time. It stays shiny because here only condensate is being generated. So the process side product generation is a very positive side effect of that process. So it's, even though if it is a lot faster, it is a lot smoother, a lot calmer. So that means for higher like volume jobs, the process quality is over a long period more stable than with the Gauss beam, where we're coming from with the legacy. You see that also here in direct comparison, the difference can't be stronger. But with 4 lasers, you can see how quick those layer times really become. And here we have, this is the part that is on display at the exam booth, where we have printed for the first time really huge quantities of material. So that is a 17 kilogram part inside the system. Now 17 kilograms of Inconel printing in only 16 hours, I think that is very, very out of this world. So the part that is on display has no contour, there's no upskin, downskin development. It was just for the very first time tried to really print as much material as possible that we could get. So it is not very beautiful, but it's a demonstrator of how much power that system really has. The part is a real part being used by KSB, and KSB had very difficulties in the past to generate and justify the business case. So when we started working on this application in about 2020, the printing time was in the range of 150 hours. So that customer had real difficulty to justify the business case. You can imagine how expensive that part was when he was printing it. I mean, 2 years later, the printing time was already reduced by pretty much 50% by introducing a new layer thickness. But still, like a couple of days printing time, that is a lot of money that goes into one component that is typically not that expensive. So with the M290 N-Light, we were the first time able to have a positive business case for the customer, but the customer was not really making money with that application, really not paying off. And then on the M3, we have demonstrated we can just print it in 16 hours. So we were cutting down the cost very dramatically. So, and if you're in these ranges of the productivity of such platforms, the getting from 17 or 18 cubic millimeters per second and per laser to maybe 20 doesn't make a big difference anymore. The next big thing for the price of the part is becoming really the powder and the process post-processing, so to say. So here we are reaching new grounds and new level. I just have to check on the time that I'm not running out of it. Also, again, here with the process side product formation, you can see this is a view on the standard processes. You see that like the powder is always contaminated. It is, it's not that great. But with the Enlight technology, even if you have higher amount of parts being generated, the powder bed looks always smooth after the processing. A second application that I brought with you is a case from Danfoss. Danfoss has a good legacy in making pumps and pump components. So this part that you see here is part of a rotary piston pump and is a legacy component. So in the former times, it was manufactured from super duplex. So the customer has had the challenge to just cut from a rod of super duplex a slice of that material, and then he's putting some bores here, and he's like milling a little bit of material away. And he has a target cost of about 150 euros, the manufacturing cost of this raw blank. We have calculated if we just take this legacy design of this old pump, where the customer for removing of the material has to spend money. If we just take this legacy design and put it onto the M300 platform, we have already the parts price matched. We are at exactly the same manufacturing cost for the blank. Of course, there comes post-machining still to the component, but the business case is not so far away anymore. So even a legacy component that's 30 years old, where you don't have to do functional integration, topology optimization, that kind of stuff, the quality is acceptable for that customer. The business case is there. Now, what we started doing is, because there was no prints, there was no fluid simulation, there was no dynamic simulation there at all, we were thinking, okay, how about, can we remove here material? And the customer said, yes, of course. So around these bores, they're just fixture holes. The intelligence is inside this component. We have a lot of possibility to remove material. And if you don't print material, I mean, your print process gets even faster, your printing time goes down, the cost per part goes down, as well as the material used in the component goes down. So we've demonstrated with the additive manufacturing, we can about cut in half by just like using smart and new technologies. And again, this part is on display. So you can go to the exam booth, and there you will find this application. You can see it in the first iteration of where we have removed material of the component. And we're still in optimization with Danfoss to remove even more material and make that business case more appealing to them. So what I want to say about this application is sometimes it is not necessary to reach for the stars, to really think about how is the best possible topology optimized component, functional integrated component, a positive business case for me, but look on your existing portfolio as well. So there might lie some gold nuggets that you can earn. Next thing that we're working with the customer is also utilizing more of the build space. So this is what we are aiming to do, really using the full process chamber. Now this is adding a lot of stress onto the entire component because we have a fill factor of over 40%. So in metal additive manufacturing, a fill factor of 40% of the build envelope is extremely high. So making a machine that can sustain that, this is something that we're working on. We are working on doing that by utilizing not only high powers, but also smart processes. So we are working a lot in the R&D department to make our processes more intelligent, that we can generate parts that have not been previously possible. And I will bring you some examples here. For instance, with process innovations. I've showed it already last year. Now we're starting to combine all of that. And I think this is really exciting because this is how a process looks typically. And this is how a process can look if you do it in a smart manner. I will just do it again for the trick of the show. I think this is very exciting. So we were talking already about process side product suppression. And now we are printing parts pretty much without any process side products at all. The reason why we've showed this on a steel part is because the effect is more dramatic. So you see the effect very clearly in the spatter formation. On the powder, it does not look as clear, but it looks a lot clearer if you see it here on the sides. So it's sorry, we'll just run the video again. So it appears not that strong, the effect, but it is there. It is really measurable in the density and the quality of your components. And you can see it also here in the part. So like already a very, very good process. This is a titanium case that we have demonstrated on. I mean, this is very low in residual porosity. We can get this even down. We can get even better than this with smart processes. So just a different image color, but you can see that the total amount of pores has been reduced dramatically. And I would conclude my presentation and my time with you with a demonstrator from Smart Fusion technology. So Smart Fusion is a closed loop technology that we've been using to optimize especially downward facing surfaces of components to make them better in the quality. But Smart Fusion has been to us also our teacher of how to make processes even better, because Smart Fusion only works if something goes wrong. But typically in a process you don't want something to go wrong. You want it to be right without having the need to correct for errors and defects. So in this case, Smart Fusion was our teacher that made it possible to build really complex geometries almost horizontally, I mean 5 degrees overhang, with a material that is very sensitive to overheating directly onto the powder blade. So this is something I think really, really great. And again, please come to the XAM booth. You can see there the parts live, and me and my colleagues, we will be there to answer your questions. If you have any and want to see the parts, I'm happy to invite you to come over and see the parts. Thank you.